Okay, in this presentation we're going to look at joint discrete random variables. So we have the joint probability mass function of x and y given in the table below. So we have a variable x and it has three possible values, a discrete random variable x, -1, 0, and 1. And likewise we have y, which can take the values 0, 1, and 2. Okay. Here we have all of the joint probabilities of each. Okay, so each possible pairing of a value of x and a value of y, what is the corresponding probability of that? For example, if the probability of x equal to 1, and y equal to 1, the probability of that is 1 in 12, okay? That pairing, okay? So obtain the marginal distributions of x and y and calculate the expected value of x, the expected value of y, the variance of x, and the variance of y. Okay, so the first thing is the marginal distributions of x, let's say. So this is essentially the row totals. Okay, so essentially what we're going to do here is add up each row there. Okay, so what we have there is 1/6 plus 1/12 plus 1/12. 1/6 can be written as 2 over 12. So 2 over 12 plus 1 over 12 plus 1 over 12, 4 over 12, and that gives us 1/3. Likewise, it's actually the same calculations here, just done in slightly different orders, 1/3 and 1/3. Okay, and likewise, doing it for the marginal probabilities of y, just get the column totals there. Okay, the same way, but just working along the columns. Add up all the columns, and you will get 1/3, 1/3, and 1/3. So essentially, this is the summation of 1/6, 1/12, and 1/12. Okay. Now, this is going to be, I'm going to do this very quickly here in this particular case, but essentially the expected value of x and the expected value of y can be deduced fairly quickly. It's essentially the expected value of x equals 0, the expected value of y is equal to 1, essentially because each outcome is equally probable. Each value of x is equally probable, each value of y is equally probable. You can work it out using this formula here. I'm going to sort of skip past that in this particular video. This is the marginals, each value of x, -1, 0, and 1, and each corresponding probability, 1/3, 1/3, 1/3. Do that for y as well, and you should get these answers here. Now, okay, so the explicit calculation. So that's how you do it by explicit calculation. It's probably okay to spot it in this case now. So what we're going to do here is, there's a slightly different approach I'm going to take here for calculating the variance. Okay, so what I'm going to do in this particular approach is there's a different way of calculating the variance of x and the variance of y. Okay, but in this video I'm just going for something else. Usually the way I would do it is the variance of y minus equals the expected value of x, squared minus the expected value of x to be squared. Now that's the way I would usually do it, but in this particular instance I'm just going to show a different approach where it's x minus x bar squared times the probability of x and sum that up. This is just a different approach to do it. Okay, so essentially here x bar is the expected value of x, is the mean here. That's the mean. So the expected value of x, that comes in here. The expected value of y, that's coming in here, that one there. Okay? So essentially what we're going to do is for each possible value of x, subtract the mean, square it, and multiply it by the probability. Here the probability in each case is 1/3. Okay, so -1 minus the mean, 0, or the expected value, square that, you get -1 squared, that just turns out to be 1. 0 minus 0 divided by 3, 0 minus 0 squared divided by 3, 0 minus 1, 1 minus 0 to be squared over 3, so that's 1/3 plus 0 plus 1/3, that equals 2/3. Likewise, same sort of calculation here down below for y. The three possible values are y are 0, 1, and 2. in each case what we do is subtract the mean. So subtract -1 from each of them, and then what we do is we square it and then multiply by the probabilities, which in this case is 1/3. So divide by 3 in other words, and we actually get the same value here, 2/3. Okay, so that's just a different approach to the one I would usually take. Okay, but you know, it's sort of good to sort of know it in case you see it in the textbook. Okay, so obtain the conditional distribution of y for each possible value of x, and hence show that the expected value of y given x being some particular value is a linear function of x. Okay, so the conditional distributions of y for each value of x are as follows. Okay, so essentially what we're doing here is we're just reforming this here. So 1/6, 1/12, and 1/12. That's 4/12. Okay. So the conditional distribution is that if x is equal to 1, and we know it's equal to, or sorry, -1, what is the probability that it is equal, y is equal to 0, y is equal to 1, y is equal to 2. Okay, so it's essentially reorganizing this information here, or so essentially what we're doing is sort of rewriting it in a way such that the totals are 1 in each case, and just making sure that we have the right proportions laid out. So given that x equal to 1, probability that y is equal to 0 given that x equal to -1 is 1/2. Okay, because it's 1/2 of the 4/12 for the joint probabilities. Okay, now you essentially can do this by inspection. It's just actually understanding what exactly we're being asked here, the conditional distributions. Okay, so the total of the conditional distributions should add up to 1, so just make sure that you have the right proportions laid out here. Okay, that's really the gist of it. Okay, so you can do it by calculation, but just actually it's a bit long-winded. For this example, you should be able to do it by inspection. Okay, so for example, here what I've done here is the expected value of y given that x equal to -1 equals the three values of y by the corresponding probabilities, add them up, and we get 0.75. Likewise for these two here, 0, 1, and 2, given that x is equal to 0. So the probabilities are 1/2, sorry, 1/4, 1/2, and 1/4, or 0.25, 0.5, 0.25. So that's equal to 1, and there we go. The expected value of y given x equal to -1, done the same way, and it is 1.25. Okay, now we have to show that this is a linear function of the expected value of y is a linear function of x. Okay, so essentially just sort of like stating it in terms of an arithmetic progression is sufficient here, or an arithmetic series, if you will. Yeah, progression. Okay, so we have -1, -1, 0, and 1. The expected value of y given that x equals 0.75, 1, and 1.25. It's essentially just to sort of demonstrate that there is a consistent increase sequentially in both. That's it, really. Okay, that's all you have to do. That's all, just to sort of demonstrate. X goes up by +1, the y's go up by 0.75, 1, and 1.25. Okay, now just say for argument's sake this was 2 here instead, and the expected value 1.50, you can that would work as well. It helps that in this particular question, just to make life easy, -1, 0, and 1 are sequential integers. Okay, now find the expected value of y, the expected value of x times y, and deduce the covariance of x and y and the correlation of x and y. Are x and y independent? Okay, so what we're going to do here is first off calculate the expected value, or the expected value of x times y. Okay, what we have to do in each case, so let's say -1 and 0, is we just have to calculate it out and then multiply it by the probability, 1/6. Okay, so it's -1 times 0 times 1/6. Then we have x equals -1, y equals 1, -1, 1, and the probability there is 1/12, and so on. So there's just a good bit of number crunching, and a lot of the numbers immediately go straight to 0. Okay, so I've actually probably done a little bit more than I should have there, so that like quite a few of them will go to 0 automatically. So essentially what we end up with is -1/12 plus -2/12 plus 1/12 plus 2/6, and that works out to be 1/6. Okay, so getting the covariance of x and y is using this formula here again. Now this is very similar to the formula I discussed previously, the one I didn't use related to the variance, but it's something very similar to that formula here. Covariance of x and y is the expected value of x times y minus the expected value of x times the expected value of y, and it works out to be 1/6 minus 0 times 1, which is 1/6. Okay, so the next part is the correlation of x and y, which is the covariance divided by the variance of x times the variance of y. So that is equal to, actually sorry, I'm missing a square root there. So that's the square root. So it's the square root of 2/3 times 2/3. Which is just equal to 2/3. Okay, so I'm back on track here. Okay, so that is equal to 1/6 divided by 2/3, which is a quarter, 1/4. So that's the answer there, equals 1/4. So it's 1/6 divided by 2/12 divided by 8/12, which is 1/4. Okay, they're not independent. Their correlations and covariance is non-zero. Okay, so we actually know that they're linear related previously. Okay, from part B, I think, actually, not part A. A couple of typos here. Now, finally, find the probability of distribution of z equals x cubed plus y minus 1 cubed. This looks awful, okay? But it's actually not really. So what we're going to do, apologize for that, is calculate the values of x cubed. Now, so I have it here as x, okay? Well, what's the corresponding value of x cubed? Okay, well, x cubed is actually -1 cubed, which is -1. Here, 0 cubed is 0, and 1 cubed is equal to 1. Okay, y minus 1 is, in this case, would be -1 cubed. That would give us -1. 1 minus 1 is 0. The cube of that, 0. 2 minus 1 is 1. Cube that, 1. Okay, so essentially what we're doing here is we're adding, in each case, -1 and -1, add them together, we get -2, -1, 0, and so on. Okay, so let's just bundle them all up. Here we have z is equal to -2. Okay, the probability of that is 1/6. So that's where we get this one here. Okay, 2/3, sorry, -1, this here plus this here, that's 1/12 plus 1/12, that gives us 1/6. 0, again, here, here, and here. and add them all up. That looks a little bit weird. Let's get rid of that. Add them all up, and we get 1/3. There we go. And that's how we do it there. That's essentially how that one is done. Okay. So we'll leave it there. That's the answer, the full answer here down the bottom, that part there. Okay, let's leave it there.